Hi everyone, today we would like to share a new active learning method, ALG, Fast and Accurate Active Learning Framework for Graph Convolutional Networks. This is a quick outline about what we are going to talk about. Before walking through the details about the proposed method, we first introduce our motivation, the preliminary about active learning, and then our methods. After that, we will end this talk with experiments and contributions. Graphs, representing entities and their relationships, are ubiquitous in the real world, such as social networks, knowledge graphs, and molecular structures. Recently, many researchers focus on developing deep learning approaches for graph data, leading to rapid development in the field of graph neural networks. Among them, the most representative method, the graph convolutional network, has achieved great success in many graph-based applications, such as node classification and link prediction. Though GCN is a type of semi-supervised method, to achieve satisfactory performance, it still requires a sufficient amount of labeled data. However, in many practical applications, unlabeled training data is readily available, but labeled ones are scarce. Here is an observation from the dataset given by our industry partner, Tencent. We observed that less than 5% of the data have labels. So, how can we learn an effective GCN with limited labeled data? An answer is to use active learning, which means to actively select some unlabeled instances to query from an oracle. On Amazon Mechanical Turk, the crowd cost is at least 5 cents per label, not to mention the expensive experts. The goal of this work is to design an active learning method that minimizes the labeling costs while maximizing the model performance. Then, we will introduce the preliminary. First, let's look at the problem formulation. The goal of active learning is to select a subset of nodes from the training set to label that produces a model with the lowest loss on the test set. In this work, we follow the setting of the pool-based active learning. First, instead of selecting all the nodes only once, each iteration, it selects a batch of unlabeled nodes that maximize the metric phi. Then, query the labels of these selected nodes from the oracles and add them to the label set. We continue these two steps until we have selected a budget of B nodes. Note that the final performance of an active learning method depends on the design of the metric phi. Then, let me introduce what the metric phi is in the traditional active learning strategies. Uncertainty sampling uses the entropy to select the instance that is the most uncertain about how to label. Query by committee defines the disagreement and selects the instance according to the principle of maximal disagreement among the committee. Information density method improves the query by committee method by adding the similarity and selects the instance weighted by the average similarity. While the previous approaches mainly focus on data which is RID, some recent researches attempt to apply active learning to graphs. Before introducing them, let's take a look at how GCN works. GCN and its variants iteratively propagate the information of the nodes to their adjacent nodes when predicting a label. 4 elements are used in the calculation of each layer, which are the diagonal node degree matrix, adjacent matrix with self-connection, the node embedding, and the learnable weight. Compared with a multi-layer perception, GCN has the ability to enhance its feature with the adjacent nodes. In recent researches, AGE applies the GCN to generate embedding and prediction for each node and select nodes to query by combining the 3 metrics. ANRMAB improves AGE through dynamically adjusting the weights of different strategies based on the MAB reward. Here, we conclude the challenges of applying previous approaches on graph. First, effectiveness and reliability. Traditional active learning strategies do not consider the graph structure. Current GCN-based active learning strategies is unreliable when the model is undertrained with few labeled instances. Then, the scalability of the GCN-based active learning strategies. Applying GCN-based active learning strategies on large graph is expensive due to substantial training costs. GCN does not scale well to large graphs due to recursive neighborhood expansion. The last is that the current GCN-based active learning strategies are unable to consider the influence of unlabeled nodes in coherence with characteristics of semi-supervised learning on graphs. In the next part, we will describe the proposed method in detail. First, we provide the overview of our proposed active learning method, ALG. Based on the design of the pool-based active learning method, there are two key parts in the framework: the adaptive measurement component that computes the importance of each node, and the selection component that chooses a set of nodes to label given their importance. Before talking about how we measure the importance of each node, we describe an observation on GCN. GCN can be approximately decoupled into a model-free feature aggregation operation and a model-dependent neural update operation. Note that the decoupled aggregation operation is independent of model parameters and can be viewed as a pre-processing process. Based on the observation, we define two metrics. First, the model-free representativeness. We apply the semi-supervised k-means on the k-step features and estimate the distance between nodes and the cluster centers. Note that this metric is independent of model parameters, so that it will not be influenced by the undertrained model trained with scarce labeled data at the very beginning. Then, the cost-effective informativeness. We use a computation-friendly MLP on the decoupled k-step features to build a committee of models. By using the approximate MLP, ALG spends less computational costs compared with the previous researches that used the original GCN. The final definition of effectiveness is the combination of the representativeness and informativeness using a time-sensitive parameter. The second observation is that a k-layer GCN can only aggregate the information of unlabeled nodes that are no more than k hops away. The set of included nodes is defined as the reception field of each node. While previous researchers ignore this characteristic of GCN, ALG explicitly takes the unlabeled nodes into consideration by considering the reception field of the labeled nodes. Based on the second observation and definition of effectiveness, we then define the effective reception field as the sum of effectiveness of each node in the reception field. Further, we propose to model the active learning problem as an ERF maximization problem. That is, to select nodes that maximize the sum of effectiveness in the reception field. However, this problem is NP-hard, so we propose a greedy algorithm that iteratively selects a single unlabeled node that maximizes the marginal gain of ERF. We also prove that the greedy algorithm obtains an ERF which is no worse than half of the optimal solution. Then, the experiments. To validate the effectiveness of our method, we conduct experiments on 4 datasets. The baselines include random strategy, 2 state-of-the-art methods, AGE and ANR-MAB. We also compare the performance of ALG with different base models. On the 3 citation network datasets, we can have that ALG outperforms all the other baselines consistently. To achieve the same accuracy, the best baseline AGE requires 2.2 times labeling cost as much as ALG MLP. And ALG MLP only needs to label about 5% of all the nodes in Cora to achieve a comparable performance trained on the full dataset. We also present the performance and runtime of each method. In the table, we show the model performance after labeling 20K instances, where K is the number of classes in the dataset. For example, we label 140 nodes on Cora because Cora has 7 classes. You can have that compared with the best baseline AGE. ALG MLP improves the test accuracy by 0.6 to 2.3%. ALG MLP achieves comparable test accuracy with ALG GCN, which verifies the effectiveness of the approximate model, inquiry by committee strategy. ALG MLP obtains a 62 to 692 times speedup against ANR-MAB. ALG MLP is 3 times faster than ALG GCN on average. As ALG supports both MLP and GCN as the base model, we want to point out that the user can select ALG MLP to balance the trade-off between accuracy and efficiency, or use ALG GCN to only focus on accuracy. We then conduct ablation study to show the marginal improvement of each strategy used in ALG. The results show that the reception field holds the largest marginal importance, and then clustering and QBC. Though the test accuracy may be affected if we adopt the approximate model for efficiency, we find that the gap is rather small. Finally, we use TSNE to visualize the reception field of both ALG MLP and AGE. The blue points in the figure refer to nodes in the reception field. Under the same budget, the blue area of ALG MLP is significantly denser than AGE's. Concretely, the reception field of ALG MLP and AGE contain 11,932 and 6,716 nodes respectively. More unlabeled nodes get involved in the training of ALG MLP, thus leading to the improvement of performance upon AGE. The last part is our contributions. ALG is the first framework addressing both performance and efficiency problems in conjunction with active learning and GCN. We are the first to propose the concept of effective reception field in active learning for GCN. Based on ERF, we further propose a fundamentally novel active learning selection criterion for GCN. By decoupling the GCN, we propose the model-free representativeness for graph-based active learning and utilize MLP to approximate GCN for reducing the runtime costs of informativeness measurements. Empirical evaluations on 4-node classification benchmark datasets show that ALG outperforms the state-of-the-art methods AGE and ANR-MAB by a margin of 0.7 and 2.3% and 0.8 to 2.9% in terms of predicted accuracy, while achieving up to 44 times and 692 times end-to-end runtime speedups, respectively. That's all for the presentation. Thanks for listening.